All right, everybody. So we're going to start with the Astronomy Regents Review Questions Part 1. This is just based on some old Regents questions for the new Earth and Space Science Regents. So it says basic answers to questions 1 through 5 on the information below and on your knowledge of Earth and space science. All right. So for questions 1 through 5, we can use all of the diagrams, all of the readings, right, to help us assist with the questions. Some questions may require the use of the 2024 edition reference tables of Earth and Space Science. All right. So remember that because time is not on our side when we're taking the exam, I would advise people to first to read the question, right? Looking at some key and then could refer back to the reading. All right. Now it says our sun is classified as a spectral class G star with a surface temperature between 5,000 to 6,000 K and an absolute magnitude, all right, of about 5. Based on this information, complete the HR diagram model by placing one X to indicate where the sun is located. Also identify the relative, right, keyword relative temperature and relative absolute magnitude of the sun as it transitions to a red giant. Okay. So just looking at a couple things, right? I see terms about the HR diagram. I see absolute magnitude. And if you're like, okay, I don't know what that means, right? There is a short reading about the HR diagram, all right, that we can scan and read here. And the absolute magnitude is a measure of how bright a star would appear if all the stars are the same distance from Earth. The brighter the star, the lower the absolute magnitude value. So when I'm also taking a look, um, when I'm taking a look at this diagram, one of the interesting things that I see here is that as it goes up, you'll see that the absolute value magnitude goes to -5, -10, and it goes to positive as I'm going down. Okay. So let's start with the first thing. They tell us our sun has a surface temperature between 5,000 and 6,000 and an absolute magnitude of about 5, right? We have to draw one X to indicate where the sun is located. Well, what did they tell us? The sun is between 5,000 and 6,000, right? They also tell us it's a spectral class G star, right? So that means that I can also look where the letter G may be, right? Right here, the sun may be in that area. I also know 6,000, right, is somewhere around here. 5,000 may be halfway, right? But we have a more better reading, just the fact that it's a spectral G class, right? So next they tell us that the sun has an absolute magnitude of about 5, not -5, but 5. So if I see it's a spectral G class and I see that as an absolute of 5, then I'm gonna mark my X somewhere around here. All right, that's the first part. Then it says change in relative temperature, change in relative absolute magnitude. When we're seeing the word relative, especially when you see the word relative, right? We're not talking about an actual numerical value of how much the temperature have changed. We're talking about has the temperature increased? Has it decreased? Has it become hotter? Has it become cooler? Right? Even the relative absolute magnitude. I'm not putting an actual number, right? The word relative means, when I look at my common regions terms, relative lets me know, where is it? Right here. It is comparing to something else. So anytime you have a question that says describe the relative this or relative that, we're comparing it to something else, right? Not a numerical value, right? Just letting me know, is it higher? Is it lower? Now what am I comparing? it says to compare, right, when the sun transitions to a red giant. So, as the sun right now is a main sequence star that we know of, and we know that the sun eventually, when it runs out of hydrogen and helium, it will eventually turn into a red giant. That means it would be in this area, right? The blue represents where the sun is right now. The red area represents where the sun will transition to. So, how did my regular temperature change? Well, let's take a look. I went from a spectral G star around 6,000 to giant's temperature. What happened to the temperature? I now see that it's going to be around the 4,000 range. So one of the changes that happens in temperature, going from a around 5 to 6,000 to 4,000 or less, is that my temperature change has decreased. All right. Or if you were to say cooler, or if you were to say lower temperature, all those would have been fine. All right. Now, how did the relative change in relative absolute magnitude, right? Remember, in the beginning, the sun had an absolute magnitude of 5, right? And now, when I take a look, the sun, well, as it goes to a red giant, now the relative magnitude is going to be somewhere less than 0. So it goes from 5 to something smaller than 5. So what happened to my change in relative absolute magnitude? The change, right? It also, oops, decreased. All right, or you can say lower magnitude value. So once again, when we see keywords that say relative, we're not looking for an actual value. We're looking for how did something change from what when we're comparing two different things. All right, so we're looking at number two. So it says, based on the information in the model, which list of the five of the sun's layers are in correct sequence to allow energy generated by fusion to eventually reach the sun's surface as radiation? All right, energy generated by fusion to eventually reach the sun's surface as radiation. So this could be a process of elimination, right? And when we look at the model, it's giving us the all the sun's layers and it's telling us what has taken place in each of the sun's layers. So according to our multiple choice, it starts with the core, which is right here, right? This is where fusion takes place. And we have to find out, right, what is the correct sequence of order, right? That energy is where that allows energy generated by fusion to reach all the way to the sun's surface. So energy that begins here and eventually reaches all the way to the sun's surface, right? So I automatically see after the core, the very next layer that I see next to the core is going to be the radiative zone, right? Energy, and it even says energy, keyword energy, right? Created in the core diffuses slowly through the plasma. So automatically that crosses out 3 and 1 automatically, right? Now I have to determine whether it's going to be the next is going to be the convective zone or the transition region. So let me take a look at the two. All right. When I see convection zone, right? We ended up through the plasma. That's where we last left off. And then I see rapid heating of plasma, right? Keyword creates currents of heated and cooled gas. And let me see the transition region. Thin, irregular layer that separates the relative cool chromosphere but from the hotter, much hotter corona. One of the things I see automatically, just visually speaking, The convective zone it looks right above the radiative zone, while the transition region is a little more farther towards like the surface, right? If you guys can see. So if the radiative zone is here, the next zone immediately after that looks to be the convective zone, right? The transition region still seems as though that it does have to pass through certain regions, right? You see here the core, the radiative zone would be right here, and it still has to pass through another and another just to get to this point here, right? So that's why my best answer is going to be from the core to the radiative zone to the convective zone as well. That's why choice four is going to be my best answer. Okay. Now, it does help if you do know, and we've done this in class where we've broken down how energy transfers from the core to the sun's surface. But you could also do process of elimination, right? Start from the beginning and work your way up. All right, so number three says the table below shows the eccentricity of the orbits of Mercury and Venus around the sun. All right, we have the planet, the eccentricity, and it says place a check mark in the boxes to indicate two statements that are correctly predicted by Kepler's laws. So we do have to have some prior knowledge about Kepler's laws. Okay, and when we look at the diagram, right, it tells us the model represents the orbits of the celestial bodies around our sun, right? It gives us some information about the region of the solar system inside the orbit of Jupiter. All right, so we see Mercury is here, Venus is here, Earth, Mars, etc. So we're going to do process of elimination for each one, okay? And remember, predicted by Kepler's laws, okay? So, um, for us to know what Kepler's laws is, and I'm going to summarize, okay? First law says planets move in elliptical orbits with the sun at one focus. So that lets us know, number one, that the planets don't orbit the sun in a perfect circle. That means that its distance as a planet goes around the sun, right? Its distance is going to change. There's going to be points where the planet will be closest to the sun. There'll be points where the planet will be farthest from the sun, right? Second law states that, and we see here, oops, sorry, I'm gonna put it right here. It says a line segment joining a planet and the sun sweeps out equal areas during equal times, equal interval times, meaning planets move faster when closest to the sun. All right. So that lets me know that a planet covers this area at the same time that it covers this area. In order for that to be true, the planet has to travel faster in order to make the same time that it travels in this area over here that you can see. All right. So Kepler's second law states, right, to summarize, when a planet is getting closer to whatever that is orbiting, it travels faster. When it's furthest away from whatever object it's orbiting, it travels the slowest. All right. And then the last Kepler's law, it says the law of harmonies, right? Which is the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit, allowing for comparison between the motions of different planets. So to summarize, all right, to summarize, the farther a planet is from the sun, the longer it's going to take to go around the sun. That's why Uranus, for example, takes an extremely longer time period to go around the sun than the Earth. Okay? So that's something to keep in mind. So now, knowing what we know here, let me go ahead and erase. Sorry. Let me clear all this little drawings out. And everything we spoke about referred to the motion of a planet. So, number one, Venus orbits the sun at a constant speed. That is incorrect because we just stated, right, that a planet will travel faster as it goes around the sun and it will travel slower when it's furthest away from the sun. That means that its speed is changing. The word constant means stay the same. But as a planet orbits the sun, it is changing speed. It is not in one speed. Mercury travels faster in its orbit when it is closest to the sun. That is true. We just spoke about that in Kepler's second law. When it's closest to the sun, right, it travels faster. Short third one. Venus' orbit is less elliptical than Mercury's orbit. Let's talk about eccentricity real quick. Okay, let's talk about eccentricity real quick. Eccentricity only refers to the shape of a planet's orbit. What does that mean? Okay, that means if, for example, Mercury, and we can't really tell here, but I'll give you an example, right? Let's say this is the sun and this is a planet. You see how my orbit, right? And let's say P for planet. You see how the orbit is stretched out, right? That means that it's very elliptical. And let's say you have the sun here. Let's say there's a planet. I'm gonna try the best as I can. All right. So you see how in this example, right, this is less elliptical, meaning it's not as stretched out. This scenario is more elliptical. We're not talking about farthest from the sun, we're only talking about the shape of a planet's orbit. So Mercury is more elliptical, its orbit is more elliptical than Venus. All right, it's more elliptical. So Venus orbit is less elliptical because it has a smaller eccentricity. So that is true. That is true. Four, the orbital speeds of both planets are affected by their masses. That is not true. They're only affected, as we spoke about, their speed is affected by how close a planet is to the sun or whatever object that it is orbiting. All right. And unlike Venus, the eccentricity of Mercury's orbit prevents Mercury from having a moon. Here's a problem with this statement. Kepler's law does not state about anything to do with whether or not the motion of an orbit relates to whether or not a planet will have a moon, right? Kepler's law is all about planetary motion. All right, it only describes how the motion of planets around the sun, right? How planets are moving around the sun, or how objects in space are moving around or orbiting another object. All right, so keep that in mind. So Kepler's law doesn't just apply to just planets, it applies to moons orbiting a planet, planets orbiting the sun, satellite that is orbiting Earth. They all follow Kepler's law. It says based on our solar system model. So pause right here, right? So based on our solar system model, which was right back here, right, where it says solar system model. So we're going to do based on that. It says if a new planet was identified that orbited the sun at an average orbital distance greater than that of Mercury, but less than that of Venus, the average speed of this planet would be what? All right, so let's break it down. If a new planet was identified that orbit the sun at an average orbital distance greater than that of Mercury, but less than that of Venus. So if we found, let's say for example, we found a new planet, right? that has a greater orbital distance, right, than Mercury, but it was less orbital distance than Venus, I'm gonna write NP for new planet, right? So that means that it would be in between Mercury and Venus, right? It would be in between the Mercury and Venus. And it says the average speed of this planet would be what? The average speed of this planet would be what? All right. So let's take a look. All right. And remember what we said about Kepler's third law. Third law states, right, that a planet, the farther a planet is from the sun, right, the longer it's going to take to go around the sun, right? That means that it'll have generally a lower average speed. Even when we look at our reference tables real quick, right? And I highlighted Mercury, Venus, and Earth in the order from distance from the sun. You'll notice as the mean or average distance from the sun increases on this column, look what we see right here. The planet goes from 88 days to 224.7 days to 365 days, right? We don't count the Earth's moon, right? They're only talking about the period of revolution going around the Earth, not the sun. But one of the things that you'll notice and you'll see the trend, right? Especially if we're not counting Earth's moon, you'll notice the farther a planet is from the sun, the longer it takes to go around the sun, right? Which means that its average speed will be slower and slower and slower. So when I take all that into consideration for this problem, this new planet that I put right here, it's going to travel slower than Mercury because Mercury's closest to the sun, but this new planet is going to travel faster than Venus, right? So when I take a look, which option tells me that this new planet is going to travel slower than Mercury, but faster than Venus? And when I take a look, slower than Mercury, I see greater average speed. Nope, right? Slower than Mercury, less than average speed of Mercury. I see that's true. And it's going to be faster than Venus. It's going to be faster than Venus. Greater than the average speed of Venus. Choice two is going to be my answer. Because it's between, this new planet would be between Mercury and Venus, it would be slower than Mercury, but it will be faster than Venus. All right, number five. It says using our solar system model, construct an explanation for why an observer on Earth can see a cycle of phases for the planet Venus. In the spaces below, write the term for choices A, B, and C that correctly complete the passage. So even though it's giving a short response, they give us the choices here. All right. Remember, you're going to have questions where even though it appears to be like short responses, there's a fill in the blank that takes place. Okay. So you're not going to write your own answers. You're going to choose one of these options right here. Okay. And it says using our solar system model, which means I'm going to refer right back to my solar system model right here. Okay. Um, and it says why an observer on Earth can see a cycle of phases for the planet Venus, right? Which means that for planet Venus, sometimes just like how we look at the moon and we see sometimes we see different lit portions of the moon, the same thing goes for Venus as well too, right? So one of the things I'm just gonna scan through the reading, right? If there's anything that lets me know anything about Venus and its phases that can possibly help me, I'm scanning. All right. It tells me Venus orbit around the sun. All right. It tells me Venus has observable phases as viewed from Earth. And it tells me the photograph shows a moon phase and Venus viewed with unaided eyes in the night sky. The inset box show Venus observed using a telescope. Both the moon and Venus are in crescent phase. Okay. Now it says using our solar system model. That means my answer, right, for me constructing this explanation, I'm going to refer to this entire model right here, right? I'm going to refer to this entire model right here. So now it's going to be true and false. So it says Venus orbits the sun, circling inside or outside Earth's orbit in about 225 Earth days. All right. So let's see if it circles inside Earth's orbit or outside Earth's orbit, right? And remember, we're focusing on Venus. So I'm going to go to my model and I'm going to identify Venus right. I'm going to zoom it in. Venus is this dot right here. All right. And I'm going to see Earth's orbit. I'm going to highlight in green. All right. I'm going to highlight in green. So, and I'm going to highlight Venus orbit in blue. Okay. So, one of the things you'll see right away, all of Venus, right, which is the blue orbit, is inside Earth's green that we see here, orbit, right, at all times. So, Venus is inside of Earth's orbit, not outside, right? If the Earth's orbit is green, Venus orbit is blue, it is always inside of the Earth's orbit. So number one, I'm gonna write, right? I'm not gonna circle, but I'm gonna write between these two options, I'm gonna write it is inside. Okay? This means that Venus is sometimes closer to or farther from Earth, while at other times it is positioned on the other side of the sea, which is the moon or the sun. It says that Venus is sometimes closer to or farther from Earth, while at other times it is positioned on the other side of the blank. All right, closer to or farther from Earth. Well, if I see, we're talking about closer to or farthest from Earth, right? Well, number one, Venus is always going to be inside Earth's orbit, right? Venus is going to be inside Earth's orbit. So, is it going to be sometimes Venus is going to be closer to, right? If we take a look, right? Venus is sometimes closer to Earth, while at other times it's positioned on the other side of the sea. One interesting note, right, that it says when we look at the observable phase of the moon and Venus, right, it tells us that this is a photograph that shows moon phase and Venus viewed with unaided eyes in the night sky. If we want to see any object, right, if we want to see any object at all, we have a better chance of seeing an object. Isn't it? We'll have a better chance of seeing the object when it is closer to us and not farther. Remember, this entire explanation is talking about why an observer on Earth can see the cycle of phases for the planet Venus. Where we don't have a better reason to see the cycle of phases if it's farther from Earth, right? Because we live in Earth. So it has, in order for us to make sense, we need Venus to be closer to see the cycle of phases, not farther from Earth. If it's too far from Earth, we're not going to see it. Okay? And at other times, it's positioned on the other side of the sea, right? If it's positioned on the other side of the moon, other side of the sun. Here's one thing that helps me. It says using our solar system model. Okay. That means that this explanation that I am constructing, I have to do it based on any sort of evidence from our solar system model, not from here, right, where the moon is discussed upon, from our solar system model, which is right here, right? So when I look at my solar system model, number one, I don't see anything about the moon, right? We do know that the moon orbits the Earth, but according to my model right now, the only thing that I can see is that sometimes Venus, right, the blue, will be closer to Earth, and there will be times where Venus will be on the opposite side of the sun, right, as it's orbiting. Sometimes the Earth will be here, and sometimes Venus will be right over here on the opposite side of the sun. All right. So that'll let us know why there are times where we won't see the phases of Venus. So I'm gonna write the sun. And choice C definitely helps us. The question helps us when we are referring to what they tell us to observe to. Just our model. All right. So these are the first five questions. All right. Make sure to like, share, and subscribe. Have a wonderful, blessed day and take care.